Imagine standing in the middle of a desert, or floating on a ship in the middle of the ocean, and still being connected to high-speed internet. No cell towers, no fiber optic cables, just a small dish, connecting you directly to satellites orbiting hundreds of kilometers above the Earth. This is Starlink, Elon Musk's ambitious project to build a $50 billion space internet empire that's changing how our planet stays online. For the first time in history, fast internet isn't limited to cities. It's reaching the most remote corners of Earth, from mountain peaks to polar ice. But how does it actually work? How can thousands of satellites move so fast and still deliver internet faster than your local broadband? And most importantly, why is Elon Musk investing billions to build an internet network in space? To understand the scale of this revolution, let's first see why we needed something like Starlink in the first place. For the first time in history, fast internet is no longer tied to cables under the ocean or cell towers on the ground. Instead, it comes from a constellation of low Earth orbit satellites, covering almost every corner of the planet. For someone living in a city, this might sound like science fiction, or even unnecessary. After all, in urban areas we already have blazing fast fiber internet and powerful 5G networks on our phones. But for millions of people in remote villages, mountains, deserts, or at sea, Starlink is not just internet. It's a revolution. It brings online education to children who never had access, it powers remote hospitals, it keeps ships connected in the middle of oceans. Of course, satellite internet itself is not new. We've been using satellites for communication since the 1960s. Traditional satellite internet providers, like HughesNet or Viasat, use satellites parked in what's called geostationary orbit. That's about 36,000 kilometers above Earth. From that height, a single satellite could easily blanket an entire continent, an impressive feat of engineering. But there was one big problem: distance. Every signal had to travel all the way up to space and back, a staggering 70,000 kilometers round trip. Even though radio waves move at the speed of light, that journey still introduced about half a second of delay every time you clicked a link, sent a message, or joined a video call. It doesn't sound like a big delay, but in online communication, even half a second is a lot. Starlink set out to change this by rewriting the playbook. Instead of relying on one or two satellites in distant geostationary orbit, Starlink uses a swarm of thousands of satellites flying much closer to Earth, just 550 kilometers up. That's about 65 times closer than traditional broadcast satellites. Because they're closer, the time it takes for signals to travel between the ground and space is drastically reduced. Latency drops from hundreds of milliseconds to just a few dozen milliseconds, fast enough to make Zoom calls smooth and gaming responsive. But this solution comes with a big challenge. Satellites this close to Earth are not stationary. They orbit the planet at about 27,000 kilometers per hour, whipping across the sky in just minutes. That means no single satellite stays in view for long. To keep you connected, your dish has to be smart enough to track satellites as they move and to hand off your connection seamlessly from one satellite to the next. So how does Starlink differ from broadcast satellites, the kind used for satellite TV? Broadcast satellites essentially beam signals one way from space to Earth. They don't need to track individual users, they just spread content over a wide region. Starlink is completely different because it's two-way communication. Your dishy McFlatface isn't just receiving signals, it's transmitting data back up into space as well. This requires highly directional beams that can precisely point at moving satellites. Now let's answer an interesting question. Starlink dishes don't move at all, so how can they track satellites racing across the sky at 27,000 kilometers per hour? The secret lies in something called phased array antennas. Think of it like this. Imagine standing in a field with hundreds of friends. If everyone shouts randomly, it's just noise. But if everyone claps or sings in perfect rhythm, the sound waves combine into something louder, clearer, and more focused. You could even aim that sound in a particular direction. That's exactly what Dishy does. But instead of people, it's thousands of tiny antennas, each transmitting radio waves in perfect sync. Traditional satellite dishes form a beam by physically shaping metal, much like a flashlight reflector directs light. A phased array, by contrast, replaces the reflector with math and electronics. Each little antenna sends its own wave, and by adjusting the phase, the timing, of those waves, the dish makes them align in one chosen direction. Where they reinforce, the beam is strong. Where they cancel, the signal disappears. The result is a laser-like beam of radio energy that can be aimed anywhere in the sky, instantly, without a single moving part. They bend invisible beams toward a fast-moving satellite. This is where Starlink completely changes the game. Starlink is like a swarm of spotlights sweeping across a stadium, with your dish electronically steering to lock onto the nearest one. The result is faster, sharper, and far more dynamic internet, but it also demands breathtaking coordination between thousands of satellites in orbit and millions of dishes on the ground. Now let's talk about the dish itself, because this is where the real magic happens. Dishy McFlatface isn't a curved reflector like traditional satellite dishes. It's a flat, layered sandwich of advanced RF and digital technology. At the top is the radome, a thin weatherproof cover that's transparent to microwaves and even has built-in heating to melt snow and ice. Beneath it sits the radiating layer, thousands of tiny copper patch antennas etched into precise patterns, designed to operate in Ku-band frequencies. These patches rest on a low-loss substrate like Rogers Row 400, supported by a copper ground plane that reflects energy upward. Just below lies the RF front end, with low-noise amplifiers to capture weak signals from space and power amplifiers to boost outgoing ones. Beam steering is handled by phase shifter chips that synchronize every antenna like a digital choir, while deeper electronics manage tracking, processing, and thermal stability. Beamforming is one of the most powerful tools in modern wireless communication. Instead of wasting energy in every direction, it concentrates signals exactly where they're needed, improving efficiency, boosting signal strength, and enabling long-distance links with relatively small, low-power antennas. Without it, Dishy would have to blast signals everywhere, wasting power and creating interference. With it, the beam becomes precise, targeted, and efficient. Now, this becomes even more interesting when we talk about beam steering. By adjusting the phase of each antenna element, the dish can tilt its wavefront and redirect the beam electronically. Unlike a mechanical dish that physically rotates, this system tracks satellites almost instantly, with no moving parts to wear out. In principle, phased arrays can even form multiple beams at once, a capability often used in advanced radar and military systems. For Starlink, a single main beam follows each satellite, but the underlying technology could scale to far more complex patterns. This is revolutionary because it eliminates slow, failure-prone motors. Instead, electronic steering operates nearly instantly and with microscopic precision. The idea was first developed for Cold War radar systems to track fast aircraft and missiles. Today it delivers broadband internet. So what's the cost of all this? To start using Starlink, you'll need the Starlink kit. That includes the dish, the router, and all the necessary cables. This is a one-time equipment cost, often several $100s. On top of that, there's the monthly subscription fee, usually between $90 to $120, depending on your country. And when you first sign up, there may also be a small activation or registration fee. Compared to fiber or mobile data, Starlink is definitely more expensive. But remember, this isn't designed to compete in cities where cheaper options already exist. It's designed for people who otherwise would have zero connectivity. For them, it's not just worth it, it's priceless. Looking ahead, Starlink and other systems are already testing laser inter-satellite links. This allows satellites to pass data between each other directly, instead of bouncing everything back to Earth. The result: faster, more efficient, and more resilient internet, a true space-based mesh network. So, is Starlink worth it? The answer depends on who you are and where you live. If you're in a city with fiber internet, probably not. Fiber is cheaper, faster, and more stable. If you're covered by 5G, that might also serve your needs better. But if you live in a rural, remote, or underserved area, Starlink might be the only realistic way to get reliable, high-speed internet. And for those people, it's a game changer. Internet from space is no longer just science fiction. It's here, it's growing, and it's changing lives in real time. The sky is no longer the limit. In fact, the sky has become the world's newest internet provider. Thank you for watching. If you found this video interesting, don't forget to like, share, and subscribe. And let me know in the comments, would you pay extra for internet directly from space, or is fiber and 5G enough for you?